Mathematical proofs. What does that really mean? Some of you think back to geometry when you were dealing with those two-column proofs. Not quite what we mean here. It's been said that proofs are like diamonds. They're hard as well as clear. So when you get a good proof, you kind of know it. We also know from our little talk about mathematics so far that that's one thing that makes not only the discipline of mathematics unique, but this HL analysis course. And that is we have to get somewhat comfortable proving things are true. Now, we can prove things are true in a variety of ways. And some of the goals that I have really in this next 15 to 20 minutes is to start to either demonstrate different techniques, styles, and methods of proof, and give you an introduction to how we can attack certain things. The other thing we want to do is to be able to give you some techniques within those techniques. How do we even set them up? How do we turn some statement that might be a bunch of words into a workable mathematical statement that we can then make use of things we know mathematically to arrive at a conclusion? So we know so far that if we want to try to prove something, it's different than just convincing someone. In other disciplines, you might be able to have a little bit of a discussion and argument, and sometimes the better person at arguing would win that argument because they were better at convincing the person. Not quite a proof. So some things can be held to a standard of proof. Some things maybe not. There's always going to be that little bit of an opinion or a little bit of gray area you might have to deal with. But for us, we want to try to get into what does it mean to have a mathematical proof that we can be 100% certain that from where we started to where we ended, we've made the right conclusion. So here we go. First of all, there are various types of proofs, and some are required in this course. Others I might just present because I think it can help. One type is a direct proof. A direct proof is something that you probably would have done in geometry, if anything. It's the deductive proof. When you start with some given information, you have some axioms, you have theorems. An axiom, of course, is being something that we kind of accept as being true without proof. And there are many, many things like that that we can discuss probably in class. And then you just use kind of logical reasoning, deduction, connections to be able to go from point A to point Z if you have to. But it's a very popular type of proof. Some of these proofs are also more derivations, where they're very algebraic in nature. Another type of proof is by contradiction. One of the most powerful, and quite honestly, I didn't really feel comfortable in this type of proof until well into my math studies. But in the proof by contradiction, we take what we want to prove true and we assume it's not true. And then by direct reasoning, we come up with a contradiction. And as long as we haven't made a mistake in any of our reasoning, the only mistake we could have made is our assumption. Now that's tricky for some people to even get a feel for, but it's a very legitimate and popular type of proof, and I'll give an example of it here in a few minutes. Another type of proof is contrapositive. Maybe not a requirement in this course, but rather helpful. This all comes back to your understanding of conditional statements. If P, then Q. Without getting too elaborate into that, we know that if we accept the statement if P, then Q is true, we can switch things around a little bit. If I switch it to where it's if Q, then P, that's called the converse, that is not logically equivalent to the original. Like, if angles are vertical, then they're congruent. That's a true statement. But if angles are congruent, then they're vertical, is not necessarily true. If you negate both parts, if not P, then not Q, that's also not logically equivalent necessarily to the original. But if you switch the P and Q and negate them, then it is logically equivalent. So back to that. If angles are vertical, then they're congruent. If we switch it, if they're not congruent, then they're not vertical. That's also a true statement. So you negate both sides and you go ahead and switch the P and Q. So if we want to prove an if-then statement, and it's hard to do so, all we have to show that if the negation of the then part leads to the negation of the if part, then the original if-then statement is true. I'm going to look at an example of that also. And then lastly, at least for now, because there are other techniques, is this thing called the principle of mathematical induction, known sometimes as PMI. This is an actual theorem itself, not so much a method, but a theorem that we use to prove things. And I'm going to produce another video within the next couple of days to give examples of just principle of mathematical induction, because by itself is a very powerful proof. But just to give you some ideas of where it can be helpful, it's nice when we want to prove something continues. The word induction or inductive reasoning tends to lend itself to seeing a pattern and thinking the pattern continues, like we've practiced in class, but really we can't be sure it continues. So the principle of mathematical induction is a great type of proof when we want to show a pattern is going to continue. So that's what we have so far. What I'd like to do next is to get into some of these examples. Now, when talking about these examples, I'm not going to be that precise in how I write things down. We will talk about some of those things in class, because I'll kind of give an overview of some of the important ingredients. But in a proof, you want to be very clear how you're starting. You want to be very clear as you write each step. Sometimes you have to justify the step if it's not obvious. If it's fairly obvious, a justification is not necessary. It's actually just part of the work. And then you have to have some type of conclusion. So some of those things I might get a little bit sloppy about, but I just want to demonstrate kind of the overall thinking process of these proofs. Right, so first one, we're going to prove something we all know, at least we think we do. The sum of the angles of a plane triangle is 180. Now, it's important that it's a plane triangle, and we'll get into that in a minute, but if I just happen to draw a triangle, and I want to show that 1 plus 2 plus 3 equals 180, this is a direct proof. And I'm going to use some axioms from geometry. One thing in geometry states that anytime I have a point not on a line, I can draw exactly one parallel. It's actually known as the parallel postulate, or some version of it. Now that we know the purple line is parallel to this base blue segment, we can make some conclusions. One is that this angle 1 is congruent to this angle I'm going to call 4. This angle 2 is congruent to this angle I'll call 5. Both of those sets are congruent because if we have parallel lines cut by a transversal, alternate interior angles are congruent. Again, that can be proven itself, but it's a previous theorem. And the rest of it I'm just going to talk through because I think you can kind of see what's happening here. We know that 4 plus 3 plus 5 add to 180. The reason being is they make a straight angle, and a straight angle is 180. But since 1 and 4 are the same, and 2 and 5 are the same, by a simple substitution, we get 1 plus 2 plus 3 adds to 180. Now, you would have to write some things down. You would write 3 plus 4 plus 5 add to 180, and then use some substitution. But before you know it, you get the plane triangle to have an angle sum total of 180. Now, this purple line, for those of you that might be thinking about that one, this is true if we're talking about a plane triangle. But there are other branches of geometry that really don't abide by this axiom. It's called the parallel postulate, and it is one of Euclid's 5 axioms, and it's been the most debated. But it turns out that we can come up with a consistent geometry if I would say there's no such thing as parallel lines. In other words, eventually this purple line and this bottom one meet. Maybe at something we call the ideal point, like a perspective. Like if you're standing in between two railroad tracks, you know they don't meet, but your eyes say they do, because you look way down, they appear to meet. The other type of geometry could be that there are many or infinite number of parallel lines to a given line. But then we have to kind of give a different definition of what a line is. So those are some things you might want to consider, but as far as plane geometry, this is a valid proof. The next one is a very common one. I think a version of this might be in your text, but we have to prove that radical 2 is irrational. Now I mentioned that one of the other things other than just proof techniques is to give you techniques to use these techniques. In other words, how can we set up a problem into something that's workable so we can actually do something mathematical with it? And this is a good example of that. What does it mean to show something is irrational? Well, that's kind of tricky. So what I'm going to do is use a proof by contradiction. So I will assume radical 2 is rational instead of irrational. What does that mean? Well, you may have understood before that rational numbers can always be written as basically a fraction, I'll call it a over b, in simplified form. So there's no common factors you can reduce. We can always reduce a fraction. So what I would do is assume that it's irrational, which leads this to be true. Again, I'm going to give kind of a skeleton proof of this, but this is a little bit derivation, but also a setup of a contradiction. Because this is true, it means that if I square both sides, that 2 equals a squared over b squared. That means that a squared equals 2b squared. Now here comes a very important part. Anything that can be written as 2 times a number, we can call even. All even numbers can be written 2 times some other number. And of course, I would have to state that a and b are in the set of integers. So what that means is a is even, or a squared. Well, if a squared is even, a is even. And I know we're way down here. I'm having to bend over quite a bit. Here we go. Okay, so a is even. Good. Well, then we're going to go a little bit different direction. If a is even, I can write it as 2 times some other number, some other integer. So that means that a can be written as maybe like 2k. Well, if a is 2k, and we look at this, that means 2k squared equals 2b squared. I just substituted 2k for a. Well, that means 4k squared equals 2b squared, which means b squared equals 2k squared. And again, all the while, k is some integer. And what does that mean? That means b squared is even. And what does that mean? That b is even. Well, without knowing anything about proof by contradiction, you just see me do a bunch of little fancy calculations and magic like my elder wand over here. But that's not really what's happening. If you picked up on it, we've hit what we call a contradiction. A is even, B is even, that can't be true. Because when I set this up, I stated that A and B, or A over B, the fraction, is irreducible. It's in simple form, so they have no common factors. Whereas if they were both even, I could have reduced it. So again, it seems like you're sneaking into the proof for some people, but it's totally valid. I assume the opposite of what I want to prove. I then reason, sometimes deductively, until I hit a contradiction of a known fact. And this is a known fact that we contradicted. They can't both be even because I stated we can always write a fraction in simple form. So we'll let that one sink in for a little bit, and we'll talk more about that, I'm sure, in class. Okay, the final one to look at is a proof by contrapositive. And I may not complete this, but I at least want to get a start, and again, kind of a scaffolding for what we can do here. I want to prove that if n is some positive integer, in this form 3k plus 2, where k is greater than 0 and k is an integer, we should always kind of qualify what the variables that we might be using are, what set they're in. Then n is not a square. Well, in a direct way, that could be tricky. So what we're going to do is turn it into a contrapositive proof, meaning that I really want to prove this. I want to prove if n is a square, then n is not in the form 3k plus 2. All right, so that's the contrapositive. I switched the if and then, and I negated them. Now, when doing this, I'm also going to show another technique. All the numbers that we know, all the integers, can be put into all sorts of little packets and groups. For example, we already know that even versus odd numbers are either 2n or 2n plus 1. We can also take all the integers and put them into 3 categories: 3n, 3n plus 1, and 3n plus 2, or 3n, 3n plus 1, 3n minus 1. We could put all the numbers into 4n, 4n plus 1, 4n plus 2, 4n plus 3. Every number will fit in one of those categories based on the remainder. So what I can do here is I consider the numbers, basically n, because it's a number, can either be 3k, 3k plus 1, or 3k plus 2. That will take care of any number in the world, any integer. So now n squared, so if n is a square, so let's square it. That's 3k squared, or 3k plus 1 squared, or 3k plus 2 squared. And then we would just take 3 different cases. This, of course, is 9k squared. So what does that really mean? Well, I could write that as 3 times 3k squared. So what that means is that it is not in that form. It's in the form 3 times a number. I don't want to use n, maybe I'd use m, where m is all of that. And again, I'm not being as formal as I probably should. The next, I would take 3k plus 1 and square it. And that's going to be 9k squared plus twice the product is 6k plus 1. But that can be written as 3 times 3k squared plus 2k plus 1, which is just 3 times the number. I'll call all of this m this time, plus 1. So it's not in this form. K and m, they're just going to be integers. And then you're going to do the same thing with this one. We square this. That's a 2. We get 9k squared plus 12k plus 4. We can take out a 3. If I make this a plus 3 plus 1, so I can get 3 times 3k squared plus 4k plus 1 plus 1. Again, I just thought of this as 3 plus 1. Factor out the 3. So all of this is just some other integer. That's that property of closure that I think we might have mentioned once in class. So this is like 3m plus 1. So all the different options led to something that's not this. Now we're going to have to let that settle also. But we'd have to have some type of closure in this, in all of these proofs. But we wanted to prove if n is a positive integer in that form, it's not a square. So the way I attacked it was that I wanted to prove that if it is a square, it's not in the form 3k plus 2. Any number can be written in one of these 3 ways, and when I square them, they all turn out to be either 3 times a number or 3 times a number plus 1. So that's the introduction to proof. There's going to be more to it. As I said, I'm going to produce a video on just the principle of mathematical induction. I'm also going to post a handout on principle of mathematical induction. When all of you are in class individually, we will talk more about some of these. I have several other examples, but keep in mind that you cannot become necessarily a master of proof. You're just going to get better at it. You can become a master of the quadratic equation. I could give you any quadratic equation, I hope, and you could solve it, whether it can be by factoring, quadratic formula, imaginary numbers, whatever. But proof, you just have to keep getting better. And the only way to do that is through experience. So that's all I have to say for this first part of the proof unit. Take it for what it is. Come to class with questions, and hopefully we'll see you soon.